So our second talk today is shooting lasers at the countryside for faster internet.
Okay. So I'm James Harrison. This is a talk on mobile mapping, which is an exciting and reasonably new field, which is starting to become accessible, almost. So I work for a company called Giga. Previously worked at BBC R&D, hacking on archives. Other things I do, I look at stars, I occasionally make things, and partly build robots and then get cancelled. Well, robots gets cancelled and I don't actually end up finishing them. Obviously, I am not an expert on any of these things I'm about to talk to you about, but I've broken enough stuff that I feel like I should probably come and share some stories. And yeah. So, a bit of background on the company I work for, because it's relevant because most of this stuff has been possible because of what they do. What we want is to give people faster internet in the countryside. We build fiber to the home networks, so we build fiber paths, new infrastructure to homes in rural areas of the country. And that means we've got to get fiber from a distribution point to properties over a very large amount of ground. We've built around 70,000 properties so far. We're doing another 300,000 or so. We are hiring like mad, so please come talk to me if you're interested. We're in Abingdon, Oxfordshire. So we basically do this sort of thing. We drive around the countryside with mole plows and that sort of thing, and we're really interested in where we can do soft dig, because doing this is really cheap and fast. And if you need to start digging up concrete and things, and that's really expensive, and we try and avoid that. So there's a pretty straightforward algorithm for this. We want to figure out where people want fast internet, and we then figure out how much it'll cost to go and build those areas, and then we go build it. Simple, right? So the first bit's pretty easy. Modeling where people want fast internet's pretty straightforward. There's lots of known data sets, and you can kind of do that. Building it's also really hard, because it turns out that digging up 10,000 kilometers of countryside is actually quite difficult. Who'd have thought? But the bit in the middle, where we figure out how much it would cost to go build these areas and whether or not we can actually go and build those areas at all, that's really interesting, because if you get it wrong, that's a big deal. But if you get it right, that lets you go and build areas that people didn't previously think were viable. And if you model that well, it's great. And the trouble with this is that existing rural mapping sucks. This isn't a dig at OS. OS are fantastic. Mastermap is the commercially available best map of the UK. Bits of it are starting to become open data now, so if you're interested in this, go and look at Ordnance Work Survey's website. They've got a great map. It's the whole country, and it's a cadastral map, which means it has no gaps. It's got a complete set of polygons that cover the entire surface of the UK. This is brilliant. But it has a code of roadside natural, which describes stuff that's by the road and that is of a natural construction, it's not man-made, and that covers a lot of things like verge, which we can dig in easy, very thick hedge, which is really quite tricky. We've had it miss things like streams and drainage ditches, and sometimes we even get dry stone walls where people have built walls, not told the OS haven't resurveyed the area in years, and we go and try and dig holes in it and realise there's a wall there. And we've had houses and things. So this is the sort of thing we've sometimes found. There's a hedge there, it's quite thick. This is a point cloud, we'll come to this in due course. Again, something where it was just missed out that there's actually a house built on the side of the road here. In the maps, this looks like a continuous piece of verge that we could just plough through. Not going to happen, unfortunately. These sorts of things are significant because they do eventually cost us quite a bit of money, and that can really affect whether or not we can go build in an area. So we send people out to go and survey an area, and it turns out that takes a lot of time and lots of people. So if you're building fiber to the home in urban areas like BT and City Fibre and other people, you're averaging about 10 meters between properties. We average 80 meters. So straight out the gate, there's a lot more stuff to do. Trying to get all that data back, you can send people out to go and look at things and try and understand the terrain and whether there are any obstacles and so on, but getting all that information back in a way that's useful, that lets us then correct those problems, is really hard. And trying to manage that much information at scale, turns out you don't want to be doing it if you can help it. Satellites are not useful for us because they can't see through trees, and lots of our routes are covered in trees, and they don't have great resolution. Not quite sure what's going on with the display, but nope. That's not happy at all, is it? Help. So while we're trying to get this sorted, aerial photography is another thing we've looked at doing, and again has the same issues with tree cover. You can get oblique imagery, which is where someone's taken a picture from the side and is looking at things sort of edge on, and that can help, but in most areas, in rural areas, it doesn't help that much at all. See if we can get this working again. Oh. Hey, okay. And Google Street View is another option that everyone goes, oh, you should use Street View and go through it and look at all the pictures in Street View. Most of the countryside, Google didn't resurvey since their original survey, so 6 or 7 years old is normal in rural areas, which isn't very useful for us. So mobile mapping is where we come to. Basically, it's a process for capturing geospatial data from a mobile vehicle with a bunch of sensors strapped to it, normally including cameras, sometimes including things like LiDAR. So in order to do that, you need some sensors. You've got to be able to figure out where they all are. You've got to build that all into a vehicle. You've got to get all that information somewhere usable and somewhere accessible and make some tools to work with that data. So the main sensors that we're talking about today are LiDAR, which is a form of laser scanning, and cameras. Cameras are not useful for spatial mapping. You can do photogrammetry, but it's really intensive CPU-wise, so it takes a long time if you've got a lot of images to get high-quality photogrammetry. And it's also quite prone to error. So we have a classic case where we drive along and we take lots of photos of verge. We think it's verge. It's actually a bank of 45 degrees, which is a real pain for us because we can't plow in that effectively. So you try and figure that out from photogrammetry, it doesn't always catch it. So there's a few things where actually doing direct observation of distance is useful for us, but cameras are really good for context. So laser scanners. Laser scanners are of two main types, pulse-based and phase-based. Pulse-based ones are usually cheaper and usually with a pretty good spatial resolution, accuracy, and so on. Phase-based ones are more accurate but have a shorter range typically. So it's a pretty simple idea. You fire a pulse of light, you wait and see for any reflections come back at that particular wavelength you've just shot a pulse out at, and you then have a think about it, figure out where all those things that you just saw were in space based on time. And so the nice thing is you can actually do detection of multiple objects with good enough scanners, that if you fire a pulse of light, say at a tree, then the light might pass through a leaf and hit a branch behind it. And you'll actually see a reflection from the leaf, and you'll see a bigger reflection from the branch, which stops the pulse of light. And this works really well for mapping verges and things, because it means you can actually shoot through things like hedges and typically catch enough of the surface behind that hedge that you can actually measure what the verge looks like below the vegetation. And you can then figure out what the vegetation looks like, how much of it there is, and so on. So the scanner I'm most familiar with and that we use is a scanner from a company called Regal. It's pulse-based. It can fire 1 million points per second, and it has a mirror in the back of the scanner, which can spin at 250 revolutions per second, so 15,000 RPM. So that spins around, and we effectively drive along with this on the back, and it spins around, and each time it spins, it's firing out a large number of pulses, which we're then capturing information from. So this gets you initially some events that are in the scanner's own coordinate system. So basically the angle that it saw it at and an X and Y offset. And once you georeference that, you get a point cloud. Point clouds are literally just a cloud of single points in space. And that gets some, each of those points will have some attributes with it, like whether or not you saw multiple echoes, or maybe it's just the point itself was a first echo, last echo. And if we want to, we can add extra information in there. We don't get any color because we're shooting in infrared. So effectively what we get is an intensity view of the world in infrared. But we can then overlay that with images to make some colored points. And usually we end up with horrible vendor-specific formats which we don't have to work around, which is no fun. So in theory, we've got a demo here, which might or might not work. Okay, I'm going to go with kind of. So this is actually a point cloud of the campsite, which I can't see to control, so this will be interesting. And so this is actually a complete scan of Easterner campsite and grounds. This has been georeferenced and colored, so we've got lots of metadata information about it. So this is the sort of output we get. This is online, by the way. If you just look me up on Twitter, I'm at James Harrison. You can find a link to this. You can download the whole data set for free. So thank you, my company, for letting me drive the vehicle around here and collect all this. So this data set is the output of about half an hour driving around site, and then about 2 weeks of fiddling around processing it. It's not usually that long, but I don't usually do this stuff hands-on. So normally it takes us anywhere between 3 to 5 days of processing to get a decent output. And the nice thing about a point cloud is that it's accurate within itself, as long as your georeferencing is reasonably good. So within a particular scan line, you might be talking about 2 to 3 millimeters of accuracy, which when you think you're driving along and doing 1 million of those measurements per second, it's pretty impressive. And you can take angular measurements, you can take distance measurements using whatever tools you like and figure out lots about the world without having to do a huge amount of work. So all of these things are pretty safe. If you start doing aerial LiDAR, that changes. Most aerial scanners will be class 4 and will burn your eyes out if you look at them on the ground. But all of the stuff we do on the ground is very safe, low power, nanosecond pulse lengths. It's all pretty good. Other stuff that you can get, if you're looking for a LiDAR sensor to hack on, Velodyne are usually the go-to answer. They have a range of quite cheap sensors around the sort of, I say cheap, they're still around £2,000 to £3,000 at the moment. That's cheap in LiDAR terms. And that is about as cheap as it gets today. Z plus F are probably the gold standard. Those are phase-based sensors, and that's pretty much the best you can get. Those are very, very expensive, 6 figures and up, quite happily. We also want to take some pictures, and if you're driving along at speed and you want to take good pictures, then you need to consider a couple of things. You want a lot of dynamic range in your images, so 10-bit or 12-bit dynamic range, which lets you basically drive along, and you imagine if you've got trees on one side of you and you've got bright sunshine on the other, you can still see detail in all of the trees down here, but you can still see the detail in the bright verge to your right. And we do some post-processing to turn it into 8-bit so we can consume it easily. And because we're driving along in mobile mapping rigs, we want to be driving at carriageway speeds, so we're trying to do 30 to 70 miles an hour. We don't want anything that's going to give us lots of tearing in the image, so we need a sensor that, rather than being a rolling shutter where the image is read off from top to bottom progressively, is a global shutter, so we can take the whole image data at once. So the other consideration is whether we're using planar cameras or panoramic. Planar cameras usually get used on mobile mapping rigs as a way of adding extra information to panoramic imagery. So you might have a detail camera looking at a road surface, particularly hanging at the back of the vehicle. Panoramic cameras are still what you need if you want good contextual images that let you kind of get that Google Street View feel, which is a big thing from a usability perspective. This data is really hard to use unless you kind of think through how you're going to access it. So most mobile mapping rigs, and ours included, use a camera from FLIR called the Ladybug 5. It's a very common panoramic camera, 30 megapixels, global shutter, 10 bits of dynamic range. And please, if you're ever doing anything with rugged connectors, never put micro USB 3 on it, ever, never. That's a weatherproof USB 3 connector. We've killed 3 so far, I think. You don't want those. Please use 10 gig base T or something. So we now need to figure out, we've got our sensors, we now have to figure out where they are at each moment in time to be able to place that information in context and to make it all line up. So we need to use a coordinate reference system. In the UK, we have the Ordnance Survey's National Grid, and that's got a good relation to all of the geodesic systems used by satellite systems, so we can refer to that quite readily and accurately. And it doesn't move over time, whereas if you try and reference things to latitude and longitude, due to continental drift, all of your measurements will be wrong increasingly over time. So about 2.5 centimeters a year at the moment. So we use these things and all things exclusively in post-processing effectively. So GNSS, GPS is one GNSS system. GLONASS, Baidu, Galileo are other GNSS systems. Those are how we figure out where we are accurately. Used to be do triangulation and things, but nowadays it's pretty much the gold standard for surveying is a GNSS survey done right. And you can get pretty good accuracy without needing any external correction sources, but still only a meter or so. If you want to get better than that, then you've got to correct for a bunch of different errors, mostly atmospheric errors. And pretty much the only way to do that is use a better antenna to get better signals and reduce the effect of things like multipath interference, use more satellites so you've got more data to work with, and use more information about what the satellites were doing while you were recording your position. So actually having accurate information about where the satellites were calculated after the fact. But the only real thing you can do to make a huge difference is to use a base station to correct errors. So something that sits stationary, so anything you measure in terms of movement you know is error, simply. We kind of care about accuracy a lot in this because when we get to processing, trying to make overlaps and things like that all make sense. If we have a more accurate trajectory to start with, then we have a much better chance of making everything line up at the end. So we're trying to aim for centimeters, not meters, and that's not an easy feat. You typically end up needing to put a base station down. The Ordnance Survey have actually got a huge number of existing base stations that run all the time, and you can get the data for. And there are commercial services that will take that and interpolate between multiple base stations to figure out a virtual base station near where you're doing your survey work, which is usually faster. And that lets you effectively figure out what the error is at that particular moment being introduced by the atmosphere and so on. And that means you can correct your position down from meters to centimeters. Now, this is all getting a bit expensive. It's getting cheaper, happily, much as LiDAR hopefully will be soon. I'll talk more about that later, but survey-grade receivers are still in the range of £10,000 to £15,000. If you're looking at cheaper systems that aren't quite survey-grade, but are still corrected with RTK, which is the way you transmit these corrections, then you are still looking at maybe £2,500. There's now a thing called the MLED Reach, which is about £700 a station. So it's starting to come down in price. A lot of the stuff that people have been doing with drones has helped that a lot. Because suddenly you need really cheap positioning because you might crash the drone. You don't want to put £10,000 a scanner on it. You can get open tools like RTK-lib for correction, which is kind of handy. And you can get the correction data from OS for free. So once you've got a rough idea of where you are in the world in absolute terms, we still have to figure out where we are in terms of our attitude of the vehicle. So as we drive around, we're rolling, we're pitching, we're turning around, and GNSS, even with multiple antennas and receivers, won't give us that dynamic view of the world to the accuracy that we need in terms of temporal accuracy and spatial accuracy. So in order to figure out where we are at any particular moment in time, bearing in mind that we're doing 1 million points per second, 250 scan lines per second, so we really do care about it being precisely timed as well as precise in space, we need an inertial system. So inertial navigation systems look like these exciting boxes here. Usually are integrated with the GNSS receiver, so there's a box that does your positioning and you have an antenna attached to it. So typically these are made with MEMS accelerometers, and those are exactly the same sort you find in your phone. There's slightly more precise versions of it, which justifies the higher price tag. And the same goes for the gyroscopes. More advanced survey systems will use fiber optic gyroscopes, FOGs. Those are much more expensive. They use a magic fiber system. They're complicated. They are really expensive to make. They're really, 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 really expensive. You're still looking at 10 grand plus for each of these things. You can still get pretty good performance out of cheap GNSS receivers and IMUs. It's good enough for doing a lot of things. If you're not doing laser data, you can use a lot of this stuff that's out there. If you're doing laser data, you still end up needing to stray into this sort of territory. So these things will be accurate enough that you can know where you are absolutely in the world. Without GNSS, for about a minute, you might get 5 centimeter accuracy still, which is amazing. We also use GNSS as a base reference, so as a time reference. So all of our sensor data is being captured and timestamped. All of our position data is being captured and timestamped. So we know at any particular moment where we were and what we captured. And all of the things like event triggers for cameras are on that common time base. So we just need to get all of our GNSS together, get rid of anything that we had really bad GPS signal or stuff we might introduce error with. We feed all of that data and the inertial data into a Kalman filter, which is a way of integrating all that information and estimating some of the internal state of the inertial system. So things like gyro bias and things that let us figure out a better solution. And we run that through a few times and we get some accurate position data out. And we're typically, to help that process, we actually drive for maybe half an hour before we start capturing any data at all, preferably on some nice fast roads with some slow corners in, and that gets us a pretty good view of what the INS is up to before we start capturing data. So what we end up from the GNSS is something that looks a little like this. So this is just in green or through to blue, estimate of the position accuracy we're getting from GPS. This is the Eastern site, so we had pretty good GNSS throughout the entire survey. And as we were driving away, we kept running the recording there, and you can see we had some dropouts. We had some periods where it was particularly poor, and those areas we typically would either exclude or just treat less trustfully in the algorithms that are processing the data. Oh, one other thing, you can see there a green triangle. That green triangle is the virtual reference station that we used to correct the data set, so it was calculated. So typically, once you've done all of this stuff, with all of this fancy hardware, you can get down to a positioning error in absolute terms that looks pretty good. And we're saying there that we're usually for XY positioning below about 3 centimeters accuracy. And we got that at 480 hertz temporal accuracy. So that gets us a lot of data to work with. We're trying to get the scan overlaid on top of our existing maps because we want to use them for enhancing our existing maps. So we're usually targeting sub-decimeter accuracy, so below 10 centimeters in absolute terms to the national grid. So I can tell you whether or not you're in one of those tiles on the floor or the next one over, or better. Trajectory processing, so figuring out that trajectory and making it as accurate as possible is where we spend a lot of time manually to try and get it as good as possible a solution, because it's going to cause us loads of issues later on in processing if we have a really bad trajectory at any point. So we're really keen to get that as good as we can. So once we've done that, we have some overlapping flight lines. This is again Eastern data, and you can see in different colors there, different bits of the trajectory that we're processing separately. And those are overlaps because we've driven the same route more than once. And you can see on this diagram, I just grab this, you can see over here we've actually got multiple posts appearing, and actually there's only one post. We're driving past that, it's the row of posts just up there, and because we've got multiple overlapping scans that have got slightly different positioning, we're recording that more than once, effectively. So if we don't correct for that, then we end up with interesting side effects like this. So this is where we've got some multiple objects appearing, and again you can see there's actually a lot of error here, and this is something due to the fact I processed the data incorrectly. If you have angular errors, then you get slightly different sorts of weirdness appearing. So the trouble with all of this is that everything, literally everything in there is proprietary standards, proprietary formats, and we have to get somewhere useful, which means we want to get outside of those vendor proprietary formats and into open formats. So we process our information, we do some basic classification of those points, so we can say that anything that's directly below where the scanner was probably ground, and then work our way out from that and try and label all the points to say, okay, this is ground, this is some vegetation, this is maybe a building, looking at things like reflectance of the points. We get rid of things like noise, so we sometimes, while we're driving along, we might scan rain, we try not to, birds, or occasionally you drive through a scan and you see this weird bird shape in the middle of space. It's just we happen to be driving past a bird that was flying past us. So we try and go through the data set and remove all of those sort of points because we're not actually interested in whether or not there was a bird there. Kind of cool, but. And we then try and align all of those overlapping passes and get everything snapped to a single surface and corrected for XY error and angular errors and so on. You're solving for sort of 9 parameters for each bit of trajectory. It's a very complicated thing, and it doesn't always work perfectly. And then we try and color the points in by taking our images, overlaying on top of those point clouds our images and positions, and then casting rays out from the images. The images are much higher resolution than the point cloud, so usually we've got a lot of pixels to work with, so we'll take an average from the nearest 3 pictures and this sort of thing. So unfortunately, the hardware is still too inaccessible for this to have really become an open source thing. Hopefully this is going to become more accessible because the cost of the sensors is coming down and more data is becoming available online. There's a great set of data for aerial stuff at opentopography.org and lots of information you can find there. I'm going to start speeding it now because I've realized I've only got, not that long left. 3 minutes left, okay. So there's lots of potential for new algorithms and stuff that we haven't really worked with yet. We generate loads of data, about 1 terabyte a day, and we store all of that, and then we do it all in S3 and use AWS for a lot of the processing because it's cheap and easy and it scales pretty well for this. So we're capturing roughly 50,000 points and maybe 2 to 3 billion points of data per day of information about the world. We will get rid of some of the photos and things because we don't need all of them, but we typically will keep the point cloud for life. We use QGIS a lot, which is our open source GIS system, and we built a plugin which lets us access this information through all of that and some custom rendering stuff, which I'm hoping will open source at some point soon. So we didn't build our own one. We bought one off the shelf from a company called 3D Laser Mapping. There are lots of other companies that do them. And so we ended up with a van that looks like this. It's bright orange because that's our thing. And in the back of the van, we have our system, which looks like this. You can see the laser scanner there, the cameras on top, the GNSS antenna on the top of that. It's on a lift, so we just raise it out of the back of the van when we're ready to start processing, and off we go. Other systems out there, things like this is the Leica Pegasus 2, and this is Trimble's MX9. It's got 2 of our scanners at different angles, so you can record more points. So it's this is the sort of stuff you get out of it. This is from kind of over there, and this is the intensity gradient. So this is showing you differences in reflectiveness between different points. So you can see here that where we were driving over was actually some tracks, and so those will reflect more brightly in infrared, so we'll get a higher return value. Interestingly, with things like trees and so on, branches will typically reflect more brightly than vegetation will. So you can actually take pretty good structural images of trees to figure out how many branches there are or this sort of thing, or just see what sort of branches are there. And you can things like removing vegetation to virtually strip a tree back, which is interesting. So the RGB stuff mostly works. You can see some up at the top here, some white pixels here where we couldn't find any color to apply, so we just guessed. And in terms of detail, there's a wire link fence somewhere down there, and you can see, you can pick up all of these individual wires, no problem at all. With a very fast scanner, you can pick up amazing amounts of detail, more exciting pictures of things being not properly aligned. So you can do some interesting things with this, like you can take height maps and use those for figuring out where you should put things in the world. But there's lots of things you can do with this data. It's really, really powerful. There are all sorts of errors that you can introduce by processing it incorrectly. So here's a slight issue where these are not obviously natural features. And we've got a couple of flight lines down here that are perfectly fine, but one that isn't, because we've not managed to get a good correction solution for that. So in that case, usually we'll just delete that flight line because we've got good ones that cover the same area. Fun things we've hit on the road. You should always check to make sure that roads are not private roads. We were warned off this particular road by a gentleman with a shotgun. We did not hang around. And you should always check the height of bridges before driving under them. So, very quickly, because I'm being hurried on, if you want to do this yourself, you can do a budget version. Panoramic cameras are now getting pretty cheap. Laser scanners are getting cheaper. Hopefully the stuff that's happening with automotive automation and self-driving cars is starting to push real change towards solid-state sensors, which will be drastically cheaper than the big expensive things we have now. And you can get pretty good IMUs and GNSS for not a stupid amount of money. Still expensive, but it's getting there. And if you don't need perfect precision and perfect accuracy, you can get a long way with what you can get off the shelf for not a lot of money today. Today, if you want to go build what we did or do those sorts of things, you're looking at £500,000 plus. If you want to do it on the cheap, you can probably do it for more like £2,000 to £5,000. Hopefully in a year or three's time, you might be looking at £500. This is awesome because it's a really good way to collect data about the world at speed and to try and take some power back from companies like Google, Apple, who are the only people who can go out and map these things at scale at the moment, and actually put it in that data in the hands of more people. If you want to play around with the point cloud data, then a link in a second, but there's some great tools in PDAL, Python, and point cloud library. Those are, if you've got those three tools, you can do a huge amount. And yeah, there's a link there for the data if you're interested. Come ask me questions. And huge shout out to Andrew Godwin, who made a complete 3D print of the campsite, which if you want to come and have a look at it, it's up here.